Astronomers tracking the skies with the Atlas Survey telescope flagged something extraordinary. An object on a hyperbolic path, inbound at impossible speed, cutting through the solar system from a direction no comet should come. Within hours, the reports grow stranger. Instead of faint water vapor, early spectra show carbon dioxide dominating its coma, and an odd nickel-rich signature where iron should be. The numbers don't fit, the geometry doesn't fit. And yet the official releases describe a routine comet already breaking apart. But behind the scenes, leaked observatory logs tell a different story. Stepwise accelerations, bursts of energy on the scale of nuclear plants, and data quietly scrubbed from public updates. If true, this isn't just another comet. It's a cover-up with consequences that reach all of us. So was Atlas natural, or engineered, and deliberately hidden? Atlas first appeared on the night of September 3, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, operating from Haleakala Observatory in Hawaii, flagged a faint moving streak. At first glance, the automated pipeline logged it as another near-Earth object candidate. But as additional images stacked in, the track showed something different. This was no asteroid. Its motion against the background stars betrayed a hyperbolic orbit, meaning Atlas was not bound to the Sun at all. Within 48 hours, the Minor Planet Center issued a circular assigning a provisional designation, 3Psi 2025 A1 Atlas. 3I marked it only the third confirmed interstellar visitor, following Oumuamua in 2017 and Borisov in 2019. Amateur astronomers quickly joined in, with confirmations arriving from Australia, Chile, and South Africa. Early brightness curves puzzled both professionals and hobbyists. The object was brightening too quickly for its estimated nucleus size, as if it carried more volatile material than expected or was being artificially energized. Atlas had been discovered, but from its first nights of observation, it refused to behave like the comets it was supposed to resemble. To grasp just how strange 3I Atlas is, the baseline matters. Interstellar visitors are vanishingly rare. The first, 1I Oumuamua, was spotted in October 2017. It startled astronomers with its elongated shape, its non-gravitational acceleration, and its silent departure back into deep space. Then came 2I Borisov in 2019, a textbook comet with a hyperbolic orbit but ordinary water ice chemistry. Two events in just over 2 years prompted debates about whether such visitors were more common than anyone had expected. But since Borisov, nothing. For 6 years, not a single new interstellar body entered the catalog, until Atlas. Its arrival so soon after two precedent-breaking objects already stretched the odds. Estimates from dynamical models had suggested Earth's sky should see perhaps one such visitor per century. Now 3 had appeared in under a decade. The probabilities dip into the realm astronomers describe as statistically implausible. To put this in perspective, the odds of spotting 3 interstellar objects in less than 10 years have been compared to winning the lottery multiple times in a row. The orbital mechanics alone suggest something unusual is happening in the solar neighborhood, whether through natural clustering we do not yet understand, or deliberate design. More troubling, Atlas did not resemble either of its predecessors. Unlike Borisov, its spectra did not show the classic water vapor signature. Unlike Oumuamua, it was luminous and highly active, bright enough for small telescopes within days of discovery. Statistically, Atlas should not be here, but statistically it also should not be doing what it was about to do. And yet Atlas was not just rare, it was breaking the rules. Atlas's orbit was locked down within the first week. The numbers looked nothing like a long-period comet disturbed from the Oort cloud. Instead, its trajectory was sharply hyperbolic, with an eccentricity greater than 1.05, meaning it was inbound from interstellar space, never to return. Its inclination was extreme, nearly perpendicular to the plane of the planets, slicing through the ecliptic at a steep angle. At perihelion, Atlas was calculated to pass just over 200 million kilometers from the Sun, inside the orbit of Mars, but well outside Earth's own path. Its velocity was another shock. At closest approach, it would exceed 56 kilometers per second, too fast for any known gravitational assist from the outer planets. Visualized against the solar system, Atlas's trajectory looked like a spear cutting straight through the inner worlds on a course that crossed critical lines of sight. By late October, it would enter a solar conjunction, passing so close to the Sun from Earth's perspective that telescopes on the ground would be blinded by glare. For a 10-day window, including perihelion itself, no direct optical observations would be possible. Just as the object reached its most interesting geometry, Earth would be unable to watch. That blackout window loomed large, and for some astronomers, suspiciously so. The first spectra of 3I Atlas deepened the mystery. Comets typically announce themselves through familiar fingerprints, bright water vapor lines near 2.7 microns, with carbon dioxide and carbon monoxide sometimes appearing in smaller amounts. But Atlas did the opposite. Data from the Atlas Spectroscopy Lab group showed carbon dioxide dominating its coma, 5 times stronger than any water signature. More startling was the elemental mix. Instead of the blended iron-nickel profile expected in vaporized dust, Atlas showed nickel lines with almost no iron at all. That imbalance is virtually unheard of in natural bodies. Nickel-rich alloys do exist in meteorites, but never in such isolation. The findings were so unexpected that peer reviewers immediately questioned calibration. Maybe the detectors were misaligned or the background subtraction was faulty. Yet multiple independent groups confirmed similar results. Observatories in Chile and Japan reproduced the same dominant CO2 line and the same anomalous nickel profile. Cross-checks eliminated the simplest explanations. The anomaly was real, but what it meant was unclear. For some, the chemistry suggested an object formed in an unusually cold and exotic environment. For others, the nickel signature raised suspicions of something else: refined metal, not native rock. The mainstream explanation leaned toward rare but natural, but the data left an opening that Atlas could not close. Its spectrum was not just unusual, it was physically inconsistent with known comet models. By mid-September, another anomaly emerged. Not chemical this time, but dynamical. Tracking stations noticed that Atlas was not moving smoothly along its projected path. Instead, it was accelerating in sudden steps. 3 distinct surges were logged, one on July 29th, another on August 14th, and a third in early September. Each coincided with a sharp change in tail color, shifting from reddish to neutral and back again. These delta pulses, as they became known, were unlike the gradual outgassing that comets usually display when solar heat vaporizes their surface ices. Instead of a steady push, Atlas seemed to fire in bursts, short, powerful accelerations that then stopped as abruptly as they began. Photometric analysis suggested the energy equivalent of nearly 10 gigawatts driving each pulse, the output of several nuclear power plants. For a natural nucleus only a few kilometers across, that figure borders on the impossible. Not all agreed on the interpretation. The mainstream view argued that localized jets, perhaps triggered by unusual subsurface chemistry, could mimic a stepwise effect. Others, more cautiously, labeled it a hypothesis, that Atlas's pulses resembled controlled thrusting, deliberate maneuvers rather than random eruptions. There is no consensus, but the numbers leave a lingering question: was Atlas moving under its own power? While independent teams debated spectra and motion, the official line stayed remarkably consistent. NASA's public bulletins described Atlas as faint, unstable, and likely fragmenting. Press releases emphasized that it posed no threat, downplaying its unusual orbit and omitting details of its chemistry. The language was cautious but dismissive, another minor comet, notable mainly for its fleeting brightness. Yet parallel documents began circulating in closed forums. Observatory logs, not included in official briefings, described the same anomalous CO2 dominance that independent teams had seen, along with the suspicious stepwise accelerations. Internal notes from spectroscopy labs warned of unmodeled behavior and requested further funding for analysis. But these entries never reached the public releases. A handful of redacted memos, allegedly, from NASA centers and partner observatories suggested a pattern of selective omission. Key data sets were flagged for internal use only, with external distribution marked pending review. Those reviews never came. When amateur astronomers cross-checked published light curves against leaked raw measurements, discrepancies emerged. Brightening episodes smoothed out, acceleration spikes missing entirely. Atlas did not arrive alone. Just days before its discovery, another object had entered the record: C-2025 R2 SWAN, detected by the Solar and Heliospheric Observatory's SWAN instrument. SWAN blazed into visibility with a tail stretching several degrees across the sky, rivaling the great comets of the past century. What drew immediate attention was timing. SWAN's perihelion was set for October 20th, just 3 days after Atlas would skim past the sun at a similar distance. Their approach vectors came from opposite corners of the sky, yet both would converge on the same solar corridor within a 10-day window. From Earth's vantage point, that corridor aligned perfectly with solar conjunction. Between October 8th and 18th, the sun's glare would blind telescopes, preventing direct observation. The critical days, closest to the Sun, closest to each other, would unfold behind a natural curtain. To seasoned orbit calculators, the odds of this geometry arising by chance seemed vanishingly small. Two bright objects arriving from separate origins, peaking together in the same blackout. Astronomers had no precedent. The comparison was unavoidable. Twin arrivals overlapping in time, just when Earth could not watch. Two visitors, opposite origins, converging when Earth could not look. With the anomalies mounting, astronomers and theorists began sorting possible explanations into three broad hypotheses. The natural hypothesis holds that Atlas is simply an exotic comet from a cold region of interstellar space. In this scenario, high carbon dioxide content explains its spectral dominance, while irregular jets of volatile material might produce the illusion of stepwise accelerations. Supporters of this view argue that rare does not mean impossible, and that unusual chemistry is bound to surface as more interstellar bodies are observed. The engineered probe hypothesis is more controversial. It suggests that Atlas's accelerations are not natural outbursts, but controlled thrusts, deliberate maneuvers. The nickel-rich composition could hint at refined material, while the pulsed energy signatures match the profile of directed propulsion rather than random venting. If true, Atlas would not be a comet at all, but a constructed vehicle. This is labeled as hypothesis only, and no direct evidence confirms it. The mission profile hypothesis ties Atlas to Swan. In this view, the two objects represent coordinated arrivals, using the Sun as a rendezvous point. The perihelion corridor becomes a natural staging ground for recharge, data exchange, or course correction. Proponents note that spacecraft launched from Earth regularly use solar flybys for gravity assists and energy boosts. The idea that a probe might do the same is not far-fetched. Each hypothesis carries uncertainties. The natural model cannot fully explain the nickel imbalance. The engineered model rests on circumstantial data. The mission theory depends on a timing coincidence that could still be chance. Yet none of them fully resolves the mystery. Atlas forces the debate into open territory between what we can measure and what we dare to propose. As Atlas approached perihelion, telescope time became the most valuable commodity in astronomy. Normally, large observatories schedule special campaigns to capture rare interstellar visitors. But this time, something different happened. Proposals requesting radar coverage from Goldstone and Arecibo's successor facilities were quietly declined. Optical imaging time was redirected to higher priority targets. Then came the blackout orders. Internal memos from both ESA and U.S. Space Command, later leaked to astronomy forums, instructed teams to suspend all active tracking of Atlas during the solar conjunction window. The justification given was routine. Instruments undergo maintenance when objects pass too close to the Sun's glare. But emails exchanged between allocation reviewers hinted at stricter directives phrased in language unusual for scientific scheduling. Phrases like non-disclosure priority and await further instruction. For 10 crucial days, as Atlas and Swan reached their closest approach, official channels went silent. No new data appeared in NASA's comet databases. The European Southern Observatory issued only a single-line update. Observation suspended due to conjunction. The official explanation: routine downtime. But internal emails tell another story. The blackout did not stop everyone. In Spain and Portugal, the Iberotracker Collective redirected their wide-field sensors toward the edges of the solar glare, hoping to catch faint light curves. Across the Pacific, amateur astronomers with modest backyard telescopes coordinated through encrypted forums, pooling their observations to reconstruct Atlas's path. At the center of the effort was Bill Gray, a veteran orbital calculator known for his open-source software used by professionals and amateurs alike. Gray called for a distributed campaign: log every flicker, archive every image, and share the raw data before it vanished. His appeal spread through astronomy mailing lists, private chat groups, and even repurposed weather satellite operators willing to test their instruments. By the second week of October, an informal web of independent observers had become the only active record of Atlas. They could not match the precision of major observatories, but their persistence created a parallel archive that the blackout could not erase. For those involved, it was less about proving a cover-up than about preserving the truth. The blackout wasn't the end. It was an invitation. The blackout meant that humanity may have missed the single most revealing hours of Atlas's journey. Any sudden breakup, maneuver, or energy surge would have unfolded in total silence. That loss of visibility is why amateur archives and leaked data are so vital. They may be the only unfiltered record we have of what truly happened. By the time Atlas slipped back out of the sun's glare, the damage was done. The official record showed only a faint, unstable comet, notable for its brief brightness but destined to fade into obscurity. Yet the independent record told a different story. It showed spectra dominated by carbon dioxide and nickel, not water and iron. It showed stepwise accelerations with energy outputs measured in gigawatts. It showed timing that placed Atlas in lockstep with Swan, both converging during the only days Earth could not watch. The cover-up, if it was one, left more questions than answers. Why omit the spectral anomalies from public bulletins? Why enforce silence during the blackout window? And why did two objects of unprecedented scale arrive almost together from opposite regions of the sky in the same 10-day corridor? Three hypotheses remain. Atlas could be natural, but rare, its chemistry born of a frozen alien nursery. It could be engineered, an object built not born, maneuvering through our solar system with deliberate intent. Or it could be part of a mission paired with Swan, using the sun as a rendezvous point. Each explanation carries its own uncertainties, but none can be dismissed outright. In the end, Atlas forces us to confront the unknown. Accident or mission? Coincidence or choreography? These questions will not be settled by silence. They will be settled by data that is already being gathered by those unwilling to wait for official answers. If you want to know what comes next, watch the skies.